So I just want to do two things. I want to make some elementary remarks about uniqueness of the algorithm. And then I want to pose what I think is a very interesting problem, which I know how to do. I don't know how to do all these problems I give, but not this one. But this problem has some ramifications, which I think will be obvious once I say the problem. And then I want to talk about how the highway plays a role. And let's do it all in 45 minutes or less, okay? So the was that? Someone say something? Someone said something. Or not. Okay, so you recall that our original wavelet was defined by, in the proof, sine of gamma was 1 over the square root of 2 phi hat of gamma over 2 e with I gamma h 0 of gamma over 2 plus a half plus. Well, let's consider the following. Consider psi u hat gamma defined as u hat gamma psi hat gamma, where u hat gamma is going to be a periodic function in L infinity of the torus. And not only that, I want it to be unimodular almost everywhere. Equal 1 almost everywhere. Well, we're assuming here I have an MRA, the whole spiel of the theorem. So in this case, psi u is in W0 as is psi, and is an orthonormal wavelet for L2 of R. That is to say, if I look at psi u and it dilates and translates and then that's an orthonormal basis for L2 of R. Now, that's not surprising. Well, maybe it's a little surprising, but not too surprising. Because if you recall, I mean, I just took that L that I had in the theorem, and that was a Fourier series. And now I'm just saying, as long as I stick that in with norm 1, unimodular, I'm going to get myself an orthonormal wavelet. So, yeah, that's a fact. Okay, and related to that, we have the following remark. And by the way, to prove that is easy. That's like an exercise. B, so again, given an MRA, Vj and phi of L2. Well, if theta is in W0, is an orthonormal wavelet for L2 of R. By that, of course, I mean that the theta sub mn's form an orthonormal basis. Okay. in particular, if tau and theta is an orthonormal basis for W0, then theta in L2 hat at gamma is equal to U hat of gamma psi hat of gamma. Psi is in star here, or asterisk, where U hat is equal to 1 and U hat is in L infinity of torus, and psi hat is as in asterisk. And so we have both ends of the, if we're given psi hat and we take any unimodular one, then that's an orthonormal wavelet. But if we have any orthonormal wavelet for L2 that's in W0, then we can write it down that way. So that's a very nice characterization. Now, there is something to prove here. It's a little more difficult than this. Again, it's at the exercise level. Why don't you put these as 2 exercises? I mean, that's well known in the literature. Yeah, of course.
Does the multiplying divider here, what can you say about LP?
What can I say about LP?
About that, yeah, using this using multiplier.
So LP, or did you say you meant higher dimensional space?
Yeah.
Oh, same sort of result. Sure. Now we're going to lose something if we get up too high into the type of matrices. So I'm not sure if it's true for all expansive matrices, but it's certainly true for the dyadic, for the let's say the dyadic wavelets in RD, for the matrix that's diagonal matrix. But, so these things are well worked. I suspect that's well worked. But I'm not 100% sure when you go to rather general expansive matrices.
How about Amanda multipliers?
Aha, good question. Again, I don't have that at the tip of my tongue, but people have worked at my tongues. At the tip of my tongue, but people have worked on that issue. That's a very good question. Hermanda, because the Hermanda multipliers are typically unimodular, and I'm personally very interested in the modular functions because in coding theory, basically you like to have unimodular functions, and you also like to look at unimodular functions whose autocorrelation satisfies certain properties. So, for example, having perfect autocorrelations in 0 every place except for coverage. So that's a good line of questioning, I would say. If you're interested in doing stuff like that, talk about those things, that'd be fine. Okay? Very, very interesting. Anyhow, there are a number of other types of uniqueness questions. So here's the problem I mentioned that this whole business with multipliers is a fascinating part of harmonic analysis. He's brought up, and there, of course, is the direction of the Hermanda theory and whatever partial differential equations, but there was a lot of multiplier work done in harmonic analysis directly, and I believe some of this stuff is still worthwhile working. So call this an exercise, but part of this exercise is to see other exercises that come from it. I've written down a few myself, but you can see that I think it's a creative exercise. So suppose Vj and phi is an MRA of L2 of R. And at least for me, I needed the following hypothesis. Assume phi is an L1 of R. And the reason I want that is I want to talk about a point value of the function. Assume phi is an L1 of R and phi hat of 0 is not equal to 0. Now we've got an associated CMF, let H0, which I'm going to write down. Let's see, do I have to do that? Yeah. I'm going to write this down as H0 hat is the associated conjugate modal filter from the MRA. Okay. Now suppose that H0 of n, 1, and H0 of n2 are not 0. And just to fix ideas, we're n1 is less than n2. And for all other n, not equal to n1, n2, H0 of n is equal to 0. Prove that H0 of n1 is equal to H0 of n2 is equal to 1 over the square root of 2 and here's the interesting thing, and n2 is equal to n1 plus 1. And phi hat of 0 in absolute value is equal to 1. In fact, verify that there exists some constant r, a real number, such that phi of t, the scaling function, is equal to a little phase shift here, e to the ir, and then translate n1 plus a half of the characteristic function of minus 1/2 of t. So basically, what we're saying is, although I'm not sure, you might not be so familiar with it right now, what we're saying is that if you have these hypotheses for MRA, then you're really going to get the higher wavelet, some slight modification of it. And this opens up a lot of problems that are interesting, where some interesting combinatorial issues arise. What's so sacred about just 2 here? The spacing, or the body, write out some other wavelets this way. So this is a very nice question. And this leads into the way I think about these things, talking about MRAs and R, etc. So let's close with that today. Okay? That's a nice problem, though. So it's a nice problem because there are a zillion other problems here, too. By looking at finite number sets where they're not zero, et cetera, what do you need in order to be able to say something about writing down what the scaling function is?
Professor,
Yeah,
are we anywhere close to, say, being able to characterize or classify all orthonormal bases over, say, L2 of R?
oh, that's, well, you asked a good question. No. Oh, are we close? I don't think we can classify all orthonormal bases at L2 of R. But, let me answer that question in the following way. At this point, we can use the MRA theorem to write down many other bases for a given MRA for L2 of R. Because we have the basis psi mn, but in fact, this might be a good time to think of the following. So I'm going to make a remark that is very relevant to what French is brought up. If you think of V0, then we can have then V minus 1, W minus 1, and we can have V minus 2, W minus 2, etc. That's what the MRA does. And so if we think of having an orthonormal basis, for W0, if we think of having, if I go all the way up, if I have an orthonormal basis that's somehow driven by the V0, then I can look at subbases and make lots of different subbases as I come down. I'll make that more explicit. And so I can make, once I have this MRA structure, I can make lots of other bases different from the original psi mn. We'll just accept that for a moment. Because of the, by doing splitting. But then what does this beg? This begs, this is like a sick tree. What you'd really like to do is fill in this whole tree. And you can do that too. And you can make millions and millions of new bases that way. And what you do is you essentially make hemlines across any level. And you take at this level, you take functions in here, form your basis, then you might go up to here. And that, when you fill in the whole tree, the amazing thing is, that's exactly what the Walsh functions are. Now, I don't think Professor Walsh thought exactly in those terms back in 1923. But basically, that's what it is. And so, the name of the game is, for any MRA, there are lots of other orthonormal bases you get that go beyond that uniqueness stuff I talked about over there. They're genuinely different orthonormal bases. There's a mechanism. And it's because of looking at this tree in a not too difficult way. And then there's a natural way of filling in this tree, where we have to give names to these things that I haven't given names to. And that leads to, as I say, infinitely more bases. And that's for any given MRA. Now, it turns out that the Haar functions, which were discovered 12, 13 years before Walsh's functions, lead to an MRA. And that when you fill in the tree for the Haar functions, what what you get are the Walsh functions. And so for a given MRA, in particular the higher ones, you're going to get many orthonormal bases. And you get that for any MRA. Now, do you get all of them? No. There are lots more orthonormal bases of them.
Like the complex exponentials, they don't have an MRA associated with them, right?
Complex exponential, you mean like the Hermite functions?
I actually think it's like a Fourier transform.
Oh, right. That's right.
Okay, so there are non-MRA based orthonormal bases, and then
Oh, yeah.
very
lots of
large
them.
families of them that are.
Well,
Okay.
in fact, we made, when we went to higher dimensions, that's one of the things we did. We made non-MRAs, which gave rise to these wavelet sets that we and other people, which gave rise to lots of orthonormal bases that are not MRAs. And then there's the thing I mentioned earlier in class tonight about this generalized harmonic analysis, which subsumes sort of the things that we did, plus the classical MRA theory, and gives rise to even more. I mean, someone's opened the spigot and you can't shut it off now. Whether you might want to shut it off, right? So, but the point is, the floodgates have been open. Okay. So let me just close by talking about the R MRA. So we're just going to define let phi be the characteristic function of 0, 1, and let V naught be equal to a closed linear span in L2 of the integer translates of phi. Okay? Why not? In particular, that means it's a orthonormal basis for V naught. And define Vj to be equal to the set of all functions f in L2 of R, such that 2 to the j over 2 f of 2 to the j t is in V0. Well, each Vj is a closed linear subspace of L2 bar. And theorem, which is not trivial, but it's not as high as what we did earlier. Theorem, Vj phi is an MRA of L2 of I. It's a higher MRA. Of the higher MRA. Well, let's just look at, so that's something I was going to prove. But we'll talk about the proof later, because I do have to cover other stuff. I mean, Wavelet frames next week, Walsh functions the following week. So, but this is a central part of the course to prove the MRA theorem before we finish tonight. But what is the wavelet one gets here? Well, we already know the answer to that because I proved, by suggestive language we know the answer. We constructed the higher orthonormal basis. But if we have an MRA, what does the wavelet look like? Well, let's go to this board and just write out some calculations. So assume the theorem for a moment. Well, how do we compute? We want to compute the filter H0. Well, what is H0? If I look at the coefficient H0 of n, remember how we did that? It's just going to be, we wrote down, we have the scaling equation. So we had the square root of 2 phi hat of 2 gamma was equal to H, capital H0 of gamma phi hat of gamma. And when we do that, because of that, we can write down the Fourier coefficients for H0 as 1 over the square root of 2, the integral phi of t over 2, because the Fourier transform of that goes into phi hat of gamma over 2 times the coefficient. And then, even though, so phi is equal to the characteristic function, 0, 1. But I'm going to distinguish here for the moment, so I'm going to put this down here. Characteristic function 0, 1 of t minus n. T. Well, when I do the change of variables here, this becomes equal to 1 over the square root of 2. And I've got the integral now from 0 to 2, because I've got to look at the change of variable here, of the characteristic function of 0, 1 of t minus n dt. Now that's something we can all integrate. That's equal to then 1 over the square root of 2 when n is equal to 0 and 1, and 0 otherwise. And look at that exercise that I wrote 2 boards over, right? Well, this motivates that exercise. So H0 of n is 0 every place except for 2 of its Fourier coefficients. And so what's H1? By the way, by one of the normalizations we did for H1, we had several options for that. But by one of the normalizations then, I have H1 of n is equal to minus 1 to the n. The way I did it with proof was n plus 1, with minus n minus 1, but I can do it this way too. H0 minus n plus 1 conjugate. And so what does that mean? That means I want to compute what the H1s are, all of them. I've got that, what's H1 of 0? H1 of 0 is H0 of 1, which is 1 over the square root of 2. And 0 is plus, I get a plus 1 over, I get 1 over the square root of 2. So this is equal to H0 of n, of 1 rather, conjugate, which is equal to 1 over the square root. If I look at H1 of 1, what do I get? Well, I get H0 of 0, which is 1 over the square root of 2, and I get a minus. Very important. So this is equal to minus 1 over the square root of 2. And then for any other n, not equal to 0 or 1, it's going to be H0 of some number that's not 0 or 1, so it's going to be 0. So H1 of n equals 0 for all n not equal to 0. And so, with that in mind, we can write down our wavelet. Remember how we wrote down our wavelet? Our wavelet now was then psi hat, so therefore, psi hat of t is equal to the sum of h1 of n, phi of 2t minus 1, and I have to have that coefficient in there, it's square root of 2. And now, if I just work that out, because phi is this characteristic function, I look at 2t minus 1 is in 0, 1, say. Maybe I have to work that out. What I get is that this is equal to the characteristic function of 0 to the 1/2 minus t minus the characteristic function of 1/2 to 1. I get the half. So the half function drops out trivially once I prove that this is an MRA. And the floodgates really do open. Once you have, and you've got Walsh's and the sky's the limit. And then you do that for any MRA. Okay. Plus, on the sidelines is this other non-MRA theory. And plus there's this theory that unites them. So the last result then is to prove that for this material, just to prove that we have an MRA. So theorem. Let phi equal the characteristic function of 0, 1, and let p be in 1 infinity. And set v0 equal to the set of all sums an and translates by n of phi, where an is in little lp. Let's see. I decided to write it out for arbitrary. And define Vj equal the set of all functions g of t equal 2 to the j over 2 f of 2 to the j t, where f is in V0. Then Vj phi is an MRA of LP of R. You can prove all of this very, very generally for RD and all that other stuff. I mean, basically, what I'll be having is that the intersection of the VJs is 0. The union of the VJs is dense in LP. And so the union of the VJs dense in LP of R, comma, the intersection of the VJs equals 0. And the translates tau and phi are a bounded unconditional basis for V0. For V0 in as a closed space of LP. So let me write that up here. This bounded, unconditional basis for V0 as a closed subspace of LP. Okay, I think I'm gonna stop. But this is not so hard to prove and beyond the exercise level. But I think for tonight I'm gonna stop. Next week we have to cover the Wavelet frames. That's an important part of the subject. And the following week I'm gonna do the Walsh functions. And the Walsh functions I may pick up here a little bit to talk about some of the business with bases and how to make lots of different bases. Got enough tonight? Okay. Get your money's worth?